Hey everyone, this is Dr. Walker. This is video 87, Mathematical Description of Waves. In this video, we're going to continue our description of waves. We have a few more quantities. The first one is the wave number. We use the letter k and is defined as 2 pi over lambda, or 2 pi over the wavelength. The next one is the angular frequency. We've seen this before. It's omega equals 2 pi over period, which is the same thing as 2 pi times frequency. So you can see that the wave number and the angular frequency look similar. One is over wavelength and one is over period. Now that we have these quantities, we can come up with a new expression for the speed of a wave. We know that it's lambda over period, but it's also equal to omega over k. If you just plug in omega as 2 pi over period, and then you divide by k, which is 2 pi over lambda, you will see that you get our familiar lambda over period. Now that we have these new quantities, we will be able to come up with a wave function that describes this traveling wave. The wave function is y is now going to be a function of x and t, not just time, but position and time. It's going to be equal to a sine of 2 pi over lambda x minus vt. We know that a is the amplitude of the wave. That determines the height of the wave here relative to the equilibrium position. And then we have a few more quantities here. Let's just briefly see where some of this comes from so that we understand it better. Look at the orange wave. The wavelength is the distance from this point to this point, one complete cycle. If you look at half of the wavelength, the distance from here to here, that's going to be lambda over 2, lambda divided by 2. Every time the wave travels lambda over 2, its position is going to be 0. So every time x is lambda over 2, we want the y position to be 0. So that's where this comes from. This 2 over lambda is going to cancel out the lambda over 2. So every time x is lambda over 2, we're going to have sine of pi, which is going to be 0 for the y. So that's where that comes from. And then finally, the vt, that's going to be the distance traveled in a certain amount of time. So if the wave is moving to the right, we subtract vt. If it was moving to the left, we would add vt. Remember, back when you were shifting sine waves back in math class a long time ago, when you shift to the right, then you subtract the vt. So this is going to be an expression for wave function. We can definitely use it, but we can also write it in a different form by using the definitions that we just learned. We just learned that 2 pi over lambda is the wave number. So that was k. And then we just learned that v was equal to omega over k. So let's put in omega over k here for v, and let's see what happens. We're going to have a sine, a sine of kx, and then the k's cancel out, minus omega t. So we're typically going to use this form of the wave function because it's more compact. So this equation describes the motion of a traveling wave as a function of position and time. The last thing for this video is the general wave equation. We're just going to touch very briefly on it. The book derives this equation for a wave on a string, but it takes a lot of math, so we're just going to skip the derivation and just give you the result. The result is that whenever you have a traveling wave, it has the form y equals some kind of function of x plus or minus vt. In our case, the function here was a sine wave, right? So whenever you have a traveling wave that has this kind of form, it's going to be a solution to this general wave equation. You may not have gotten to this in your calculus class yet, but this is called a second order partial differential equation. And so it describes the motion of these traveling waves. In the homework, what you're going to have to do is you're going to be given a traveling wave that has this form, and then you'll just have to plug it in on both sides of this general wave equation to show that they indeed equal each other. You're going to take the second derivative with respect to position on the left, the second derivative with respect to time on the right. We're going to see this wave equation again when we get to physics 2 and we're talking about electromagnetic waves. So this here is just a brief introduction so that this doesn't look like a foreign language when you see it again later.